Welcome to today's lecture. Myself Tukur Gupta from Electronics and Communication Engineering Department. I am going to cover the lecture series of 5 complex topics in the subject Fundamentals of Electronics Engineering. Subject code is BEC 101. Today I will discuss the special purpose diodes from Unit 1. So the contents of today's lecture will include the 4 types of special purpose diodes. We have majorly 5 photodiodes, 5 special purpose diodes, that is photodiode, light emitting diode, tunnel diode, liquid crystal display and varactor diode. Today I will discuss 4 important special purpose diodes, that is photodiode, light emitting diode, tunnel diode and varactor diode. Let us start with the photodiode. A photodiode or a photodetector is an optoelectronic device that absorbs optical energy and converts into electrical energy. So, what is the purpose of this diode? That this will absorb the photonic energy, that is the optical energy, and it will give the electrical energy. So, by absorbing the photons, it will give the current. So, that is the electrical energy. So, how is it designed? So, it is designed to operate in the reverse bias. So, what is the reverse bias condition? When in a diode, the cathode of the diode is connected to the positive terminal of the battery and anode of the diode is connected to the negative terminal of the battery. That is the condition of reverse biasing. So, photodiodes are made to operate in the reverse biased condition. Then only it will have a depletion region and the photons will get absorbed in that depletion region. The more the photonic energy gets absorbed in the photodiode, the larger will be the current produced by it. That is, the larger will be the electrical energy. So, these diodes have a slow response time when the surface area of the photodiode increases. So, this is the symbol of photodiode. Like we can see, here is the photons being absorbed in the diode in the depletion region, and this is the anode and this is the cathode. So, what is the process? It consists of the 3 steps, that is the absorption, transportation and carrier collection. So, absorption of optical energy and generation of carriers is the first step. Then when the optical energy is absorbed, so it will lead to the development of generation of carriers, that is the electrons and holes. Because the more the optical energy gets absorbed, the more the covalent bonds that get broken, and so it leads to the generation of carriers. Then when the carriers are produced, what will happen? They will get transported due to the high energy in them. So, transportation, second step is transportation of photon generated carriers across the absorption or the transit region without the gain. Next, the last step is carrier collection and generation of a photocurrent which flows through the external circuitry. When the carriers get transported, they move from one place to other. What will happen? They will lead to the generation of current, the creation of current. So, through the external circuit, this current flows. This is how the absorption of photons gets converted into the electrical energy, into the current flow. So, this is the main process of photodiode. So, here is the detail. Let us have a quick review. In reverse biased condition, the minority carriers generated are recombined before they reach the junction. Yes. So, therefore, no current will flow when through the junction. Now, what we do? We provide the photo energy, that is, external energy should be applied at the depletion region to increase the population of minority carriers and thus increase in the current flow. To overcome this problem, a special diode, this is the purpose of the photodiode, that normally without the absorption of photo energy, carriers are there, so that the current will be produced. But when we provide the photonic energy to the diode, then under the reverse biased condition, then only the minority carriers are generated and more carriers are generated, and thus it leads to the current flow. So, photons or light is used as external energy to generate more number of minority carriers in the case of photodiode. So when a photon of ample energy strikes the diode, it makes a couple of an electron hole. This mechanism is called inner photoelectric effect. Therefore, holes move towards the anode and electrons move towards the cathode. Okay, so they get attracted to the opposite polarity. So the holes will move towards the anode and electrons will move towards the cathode, and a photocurrent is generated. This is known as a photocurrent because it is developed due to the photon energy. When no light is supplied to the reverse biased photodiode, it carries a small reverse current due to the external voltage. This is called electric current. So under the reverse biased condition, without the application of photonic energy, that is the photo energy, what is the condition? It's a normal condition as any reverse biased diode. So the current produced in that scene is known as the reverse saturation current, normal reverse current. So that is also known as the dark current, denoted by I lambda. The total current through the photodiode is the sum of dark current and the photocurrent. So the one is the current that is produced due to the minority charge carriers without the photon energy. Another one is the charge carriers due to the application of photonic energy. So the total current in the photodiode is the sum of both the types of current. So this is the diagram that is showing the working that I have explained just now. Here is the incidence of the photons in the depletion. This is the depletion region. This is the depletion region on which the photons are incident, and this will lead to the flow of current. So we can see the current. We can also see that this is P type, this is N type, and P type is connected to the cathode, that is the negative terminal, and N type is connected to the positive terminal. So this is connected in the reverse bias. Now, how will the current increase? This is the dark current. Okay, this is the dark current, that is the minimum current. Then as we increase the photonic intensity, with the increase in the light intensity, the current increases. So this current is higher than this one because we are incident, because the more photonic energy is incident in this case. So this is how, with the increase of the photonic energy, the current flow increases. So there are majorly three types of photodiodes, that is the p-n junction diode, pin diode, and avalanche photodiode. Avalanche photodiode is the best diode among all. So we will not go into details. So these are majorly three types of photodiode. Among all the three photodiodes, p-n junction and pin diodes are the most widely used because of their better characteristics as compared to the other diode. Applications of photodiodes: compact disc players, smoke detectors, space applications. Photodiodes are used in medical applications such as the computed tomography, instruments to analyze the samples, and pulse oximeters. Photodiodes are also used for optical communications. The most widely used, and that is the mostly the photodiodes are used in the optical communication applications. So this is the one of the best applications of photodiodes. Photodiodes are used to measure extremely low light intensities, because even a low light intensity can produce can result in the effect of current. So that's why these are used in the detection of the light intensity, low light intensity. So here is the next special purpose diode, that is a light emitting diodes. It's a diode that gives off visible or invisible light when energized. So the function of the LEDs is just opposite to that of the photodiode. In the photodiode, what we were doing, we were applying the photonic energy, that is the okay, and then the current was flowing. But here what we are doing, that the light is being produced as the output. So so this works in the forward biased p-n junction. Here there is within the structure and primarily close to the junction recombination of the holes and electrons. So what is happening? Always there is a recombination between the holes and electrons, and so in this case, whenever the electrons and holes recombine, so what is happening? Whenever the holes and electrons recombine, they move from the higher energy level to the lower energy level. Due to that, they will release a sort of energy, a form of energy. In this case, that form of energy is the light. Okay, so depending upon the energy gap, depending upon the wavelength of the light that is being produced, its color is decided. We will see in the further slides. So, in this recombination requires that the energy possessed by the unbound free electrons to be transferred to another state. In all semiconductor p-n junctions, some of this energy is given off in the form of heat and some in the form of photons. So, it depends that what type of materials we are using. So, in this light emitting diodes, the materials that we are using are the direct band gap semiconductors, that is a gallium arsenide phosphide. So, these are certain semiconductor compounds. By using them, we can generate the light as the output. But in the case of germanium and silicon, no light energy is produced as the output. So, this is mentioned in this slide. In silicon and germanium diodes, a greater percentage of the energy converted during recombination at the junction is dissipated in the form of heat. This is what I explained just now, that due to the indirect band gaps in the silicon and germanium, we are not able to get the light as an output. Only the heat is generated in these cases. So, if we want to get the light as the output, we have to use the materials, that is the gallium arsenide phosphide, because these are having the direct band gap in their structures. So, for this reason, silicon and germanium are not used in the construction of LED devices. But on the other hand, diodes constructed of gallium arsenide emit light in the infrared zone during the recombination process at the p-n junction. So, even though the light is not visible, infrared LEDs have numerous applications where visible light is not a desirable effect. Like we can see in the remotes, we do not need the light effect, but we use the infrared lights. So, these include security systems, industrial processing, optical coupling, safety controls such as on the garage door openers, and in the home entertainment centers, where the infrared LED, that's the light of the remote control, is the controlling element. So, in that cases, we don't use the lights, but the infrared light. So, this is the working of LED. So, we can see that here is the as the carriers are moving, these are recombining. So, they will move from the higher energy level to the lower energy level during the recombination, and so the light will be emitted as the output. So, this is the symbol of LED. This we can observe that this is just opposite to that of the photodiode, because here we can see the light, that is the photons being emitted from as the output. This is the light response. The frequency spectrum for infrared light extends from about 100 terahertz, and with the visible light spectrum extending from about 400 to 750 terahertz. So, it depends in this spectrum where the light is lying. So, if it is lying in that range from 400 to 750 terahertz, then we will get the visible light. But if it is lying in the infrared region, then we will not get a visible light. So, what is the relation between the wavelength and the frequency? Lambda is equal to C upon F. So, where C is the speed of the light, F is the frequency in hertz, and lambda is the wavelength in meters. So, this is how the relation is established. Further, we can see that this is the energy gap. So, depending upon the energy gap, we will get the lambda, that is the wavelength. So, depending upon the energy gap, like this is the energy gap. Now, here the charge carriers are moving from here to this level. So, this is the energy gap. Depending upon this energy gap, we can find this relation Hc upon lambda. So, our lambda will depend upon energy gap. Depending upon the energy gap and indirectly depending on the lambda, we will get the light of the color. So, the wavelength and the frequency of the light of a specific color are directly related to the energy band gap of the material. The light intensity of an LED will increase with the forward current until a point of saturation arrives, where any further increase in current will not effectively increase the level of illumination. So, this is how the LEDs work. Next is our tunnel diode. This is the third important special purpose diode. So, the important point here is that it is heavily doped p-n junction diode, in which the electric current decreases as the voltage increases. In tunnel diode, electric current is caused by tunneling. Here, what is the tunneling? That the electrons, the charge carriers will move directly they will recombine directly. Here what is happening? Due to the heavily doped p-n junction, the valence band of p type comes in alignment with the conduction band of n type, and this is how the tunneling is being done. The tunnel diode is used as a very fast switching device in computers. It is also used in the high speed, high frequency oscillators and amplifiers. This is the symbol of tunnel diode. A tunnel diode is also known as the Saki diode, after the name of the person who invented this. The operation of tunnel diode depends on the quantum mechanics principle, that is on the wave property of electrons. This is known as the tunneling. In electronics, tunneling means a direct flow of electrons across the small depletion region from n-side conduction band into the p-side valence band. Why this is happening? Because both the bands come into alignment with each other due to the high doping. So this is the only cause of tunneling being done in this diode. In tunnel diode, the p-type and n-type semiconductor is heavily doped, which means a large number of impurities are introduced into the p-type and n-type semiconductor. This heavy doping produces an extremely narrow depletion region. So due to the heavy doping, because as we know that with the increase in doping, the width of depletion region decreases. So with the very heavy doping, the depletion region width is very narrow in the case of tunnel diode. And due to this very narrow depletion width, the valence band of p-type and the conduction band of n-type material comes in the alignment, and the charge carriers directly move from one region to another. And this is how the tunneling takes place. This is the main working of tunnel diode. So this heavy doping process produces an extremely narrow depletion region. The concentration of impurities in tunnel diodes is 1000 times greater than the normal p-n junction diode. That's why it is one of the best known special purpose diode. This is the diagram which is showing the condition how this transfer takes place through the tunnel. The depletion region of tunnel diode is very small, as I have already told you, it's in nanometers. So the electrons can directly tunnel across the small depletion region. This is how the electrons move from one region to another. So this is the barrier. As we can see that this is very thin. So electrons are tunneling through the barrier. This is the equivalent diagram. So here the diode can be represented as a capacitor and resistor in parallel, and then the whole this arrangement is in the series with resistor and the inductor. So in the tunnel diode, what is happening, that the current will increase very rapidly up to a point. This is the peak point, and from then it goes down slowly. It starts decreasing, and then at certain point, this is known as the valley point, and this from here onwards it will behave like a conventional diode, like the normal diode. So this is this is known as the tunneling current, and here it is increasing rapidly, and up to this is the peak point. What are the advantages? It has got the long life, high speed operation, low noise and low power consumption. Disadvantages are it cannot be fabricated in the large numbers. Being a two-terminal device, the input and output are not isolated from one another. So these are few disadvantages. If we talk about the applications, these are used as the logic memory storage devices. These are used in the relaxation oscillator circuits, in ultra high speed switch as well, and in FM receivers. So these are certain uses of tunnel diodes in different applications. Lastly, we will talk about the varactor diode. So as the name is indicating, it is the variable capacitor, that is varactor diode. This is a p-n junction diode whose capacitance is varied by varying the reverse voltage. As we can see that if we talk about the p-n junction diode, the p-n junction can be seen just like a capacitor. There are the two plates, p-type and n-type, and between them there is the charge region, that is a depletion charge region. So that behaves as the dielectric medium. So it behaves like a capacitor. So diode can be depicted as a capacitor. And when we give it a reverse biased, this capacitance increases. So, varactor diode is also sometimes referred to as the varicap diode, tuning diode, variable reactance diode, or variable capacitance diode. This is the symbol of the varactor diode. Here the parallel plate capacitor is being depicted. This is the anode and this is the cathode of a diode. The junction capacitance is inversely proportional to the width of depletion region, as we know that if we increase the if the width of depletion layer is less, the capacitance will be more, and vice versa. So if we need to increase the capacitance of the varactor diode, the reverse biased voltage should be decreased. It causes the width of the depletion layer to decrease and resulting into the higher capacitance. Similarly, increasing the reverse bias voltage should decrease the capacitance. This ability to get different values of capacitances just by changing the voltage applied is the biggest advantage of this diode. So, just by increasing or decreasing the applied voltage, we can increase or decrease the capacitance. So, that is why it is known as a variable capacitor, because the capacitance depends upon the applied voltage. This is how the relation is established, that is the CT is equal to K by VT plus VR raised to power n, where K is the constant determined by the semiconductor material and construction technique. VT is the knee potential as defined, and VR is the magnitude of the applied reverse bias potential. VR is the reverse biased potential. VT is known as the knee voltage of any diode, that beyond this the current will increase and the diode will start conducting. N is half for alloy junctions and 1/3 for diffused junctions. So, this is how the relation is established between the applied voltage. VT plus VR is the applied voltage and C is the capacitance. This is the equivalent circuit of varactor diode. Here we can see the capacitor is in parallel with the resistor and the whole arrangement is in series with the inductor and the resistor. So, this is the equivalent circuit of varactor diode. So, that was all for the varactor diode, and as we see from the relation, from this established relation, that capacitance is inversely proportional to the applied voltage. So, this graph is showing that as we increasing the voltage, the capacitance is decreasing. This is the relation between the applied voltage and the capacitance. What are the applications of varactor diode? It can be used in frequency multipliers, it can be used in parametric amplifiers and in voltage controlled oscillators. So, this was all about the varactor diode. So, in this lecture we talked about the four major special purpose diodes, that is the photodiode, LEDs and tunnel diode and varactor diode. All the four special purpose diodes have their respective applications in different fields. That's all for today. Thank you.